So when the power series is a geometric series, it's easy to find the interval of convergence since we just know that the absolute value of the ratio is less than 1. So when we have a power series that is not geometric, most of the time we can use the ratio test to find the interval of convergence. So remember, in the ratio test, we take the limit as n approaches infinity of the absolute value of the n plus 1 term over the nth term. And the series converges if this limit is less than 1. So we use the ratio test here. If we plug in n plus 1 for n, we'll get x to the 2n plus 3 over 2n plus 3 factorial. And we ignore this negative 1 to the n. Since we're taking the absolute value, it'll always just be 1. So simplifying this limit, we can split this up into x squared times x to the 2n plus 1, because the exponents add up to 2n plus 3, and then that allows us to cancel out these terms. And so in the end, we just get x squared over a bunch of n terms. And this limit will always equal 0, because the bottom is going to infinity, while the top is just x squared. It's not going to be able to catch up with the bottom. So for any value of x, this limit will equal 0. And therefore, the power series converges with any value of x. So the interval of convergence is going to be from negative infinity to positive infinity, and the radius of convergence is infinity. So in this power series, using the ratio test, we find that the ratio simplifies to n plus 1 times x minus 3. Now, the only way that this is not going to go to infinity is if this term equals 0. So in that case, this whole thing is just going to be equal to 0, which is obviously less than 1. So x has to equal 3 in order for this power series to converge. So the interval of convergence is just 3, and the radius is 0. So for this one, we do the ratio test, and we simplify it, and we see that we have these n terms on the top and bottom, and their coefficients are x minus 5 and 2. So remember, when we have the n with the same degree here to 1, the limit as n approaches infinity is going to be the ratio of their coefficients. And so x minus 5 over 2 has to be less than 1 in order for this series to converge by the ratio test. So therefore, x minus 5 must be less than 2. So then we can solve for the interval of convergence, which is going to be from 3 to 7. But we also need to check these endpoints, when x equals 3 and x equals 7. Because in those cases, the limit, this is going to be either negative 2 or 2, and the limit will equal 1. And remember, if the ratio test leads to 1, then it's inconclusive. It doesn't tell you if it converges or diverges. So we have to test the endpoints separately. So when x equals 3, then this series, this part is going to be 3 minus 5, or negative 2 to the nth power. And so splitting this up into negative 1 to the nth power times 2 to the n, we can cancel out these 2 to the n's. And notice how for any value of n, these two things are going to be, one of them is going to be positive 1, and one of them is going to be negative 1. So overall, it's always going to be negative 1. So this can be written as negative 1 over n, which is the divergent harmonic series. So when x equals 3, the power series diverges, so 3 is not part of the interval of convergence. When x equals 7, we just have 7 minus 5, or 2 to the n, and then these cancel out. And then we just have the alternating harmonic series, which is convergent because it's decreasing and the limit as n approaches infinity is 0. So when x equals 7, the power series converges, and therefore it's part of the interval of convergence. So we have x is greater than 3 and less than or equal to 7. And then the radius of convergence is 2, since we're centered at 5. So if we have a function that we're representing with a power series, and the radius of convergence of this power series is greater than 0, then the derivative or antiderivative of the function can also be represented by the derivative or antiderivative of the power series, and it's going to have the same radius of convergence. So say we have this function f of x represented by this power series, where c is the coefficient and a is the center. And so the derivative of the function can be represented by the derivative of this power series. So you're differentiating with respect to x, and you basically pretend that n is a constant. So by the power rule, we just bring the n down, and then subtract 1 from the power. We just have n times c n times x minus a to the n minus 1 power. And notice how the index got shifted up 1. Now it starts at n equals 1. And this is because, in this original power series, the first term, when n equals 0, is just going to be the coefficient c sub 0, which is a constant. And, when we take the derivative of a constant, it's going to be 0. So if we studied the index at this derivative, at n equals 0, the first term would just be 0. So to avoid that 0 term, we just move the index up 1. And you don't really have to do this, but if you don't do it, your first term is just going to be 0. And then the integral of this function is going to be equal to c, but when we take the indefinite integral, we get that c plus the integral of the power series. We just add 1 to the power, n plus 1, and divide by the new power, which is n plus 1. Okay, so if we want to find the power series for this function, 1 over 1 minus x squared, now all we have to do is recognize that it's the derivative of 1 minus 1 minus x. 1 over 1 minus x. And so this is easy to find the power series for, since it's a geometric power series, where a equals 1 and the ratio is x. So the power series is just x to the n power. And so the function, the derivative of it, we just differentiate the power series. So we bring down the n and subtract 1 from the power. So it's just going to be n times x to the n minus 1 power. Another way you can think about it is you're just differentiating each of these terms in the power series. So have 0 plus 1 plus 2x plus 3x squared, and so on. And so we can find a power series for the inverse tangent function because it's just the antiderivative of 1 over 1 plus x squared. When we integrate this function, we get inverse tangent. So this is again a geometric power series, where a equals 1 and the ratio is negative x squared. So we can easily integrate this. So we get c plus the integral of this, which is we add 1 to the power, 2n plus 1, and then divide by that new power, And then we can solve for c by plugging in any value of x. For the easiest one is obviously x equals 0. So if you plug x equals 0 in, we get the inverse tangent of 0 is equal to c plus 0, since this is going to be 0, so the whole thing is going to be 0. So we get that c is equal to 0.